two special functions. The first is called density function, right? Probability density function. And the definition will be given. Okay, so this is a probability density function with mean value equal to mu and standard deviation is sigma. Okay, and the corresponding function in math actually is called norm PDF. Okay, and in math the function needs three arguments. The first is x specific realization, but we know in math a function can have a vector as its argument. So usually we can use a vector for the arguments. And also you have mu and sigma, okay? So that's PDF. And then we can also define, distribution function. Unfortunately, the distribution function for Gaussian does not have a closed form, so which means we still have to use the integral for this rotation. In other words, fx here, which is what? The probability that's equal to a specific realization. So this will be actually from minus infinity to x, all right? And then this should be what? Fx x dx. Actually, I should use different dummy variable. Let's use, say, y. Okay, so y will be a dummy variable in this integral. So it will be something like this. Y minus mu squared to sigma squared dy. Okay? So in other words, there's no closed form for this integral. Right? In other words, we have to use numerical methods to evaluate this integral. And the corresponding method function is called norm CDF, cumulative distribution function, okay? So which also has the same input arguments, so which will be, say, x, mu, sigma, okay? All right, and if you pay attention to solutions, we also need to use the inverse function of distribution function. Because here, distribution function is used to determine the probability, right? So the event when this random variable is less equal to this specific realization. Put another way, we can say this guy equal to a probability, right? And then, like the question we have in the homework, the probability is given, right? We'd like to determine the corresponding realization. In this case, we have to use what? X equal to the inverse function of this distribution function, okay? And the corresponding function in math is called norm INV, okay? In this case, this function actually has three arguments, and it's very similar to these two functions regarding their input argument, except x replaced by what? Probability. Okay. Okay. So these are those functions actually we can use to solve specific practical questions. Of course, I cannot test you guys, using those functions in the test, but those functions could be useful to solve some probability questions, okay? Which not necessary from our class, might, from some practical projects you might be involved, okay? All right. If you have any, like say, doubts regarding solution where this function is used, so we can talk maybe next time. Okay, so basically this function will be used to determine the specific realization when the probability is given. Okay. I mentioned, the reason why Gaussian distribution is because of a very famous theory which called central limit theory. Okay, so basically, central limit theory says if we have, like say, multiple random variables, okay, they follow, identical distribution independently. Okay, it doesn't matter what kind of distribution they follow. Okay, so in other words, we have x1, x2, blah blah blah, xn. Okay, and they follow the same distribution. Okay, and also all these random variables independent. Okay, and we call these random variables, say, IID. Okay. One I represents what? Independent. Second I represents what? Identical distribution. Okay. For example, I'm going to show you, like say, when x follow, say, uniform distribution. Okay. And I'm going to, try it again in simulation. Basically says the average actually among these random variables would follow a Gaussian distribution. Okay, and here we need to figure out the corresponding mean value as well as the standard deviation. In order to do so, we just need to apply, like say, the linear property regarding the mean operation here. In other words, how can we determine this? The mean here. Okay, and this will give us the mean value of xk. K will be from 1 to n, and the n will be taken out. So this will give us, say, because I just mentioned, each of these n random variables will follow identical distribution. In other words, each mean value should be same, right? So as a result, let's say this exk equal to, say, mu. So it's identical among these n random variables, and obviously this equal to what? N mu over n, which should be mu, right? Okay. In other words, the mean value for this average should be mu. Okay. So how about the variance? And also, let's say the variance of xk is sigma squared. Okay. And then we know for the variance, x1 plus x2 plus blah 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 xn over n. All right. And this actually will equal to what? Equal to, say, variance of x1, and n will become what? N squared. Again, this is because these n random variables are independent. So plus, say, variance x2 over n squared plus blah 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 variance xn over n squared. And this will give us n sigma squared, right? Because each of them has the same variance over n squared. So it's what? N squared over n. Okay? So this will be the variance, for this average. In other words, the standard deviation will be the square root of this guy here. So this will be what? Sigma over what? Okay? And it's part, so actually we can verify, this conclusion from a pure mathematical point of view. But as an engineer, we are more interested in, let's say, instead of proof, let's just try to verify using simulation. Before we do that, let me just formally introduce the uniform distribution. And here this is Gaussian, right? For the uniform, let's say if a random variable follow a uniform distribution between A and B on the interval from A to B, okay? And then this will be the probability density function what equal to actually 1 over B minus A, and when x is between A and B, and 0 otherwise. Okay? And now let's just try to determine the corresponding mean value and the variance. So, and the mean value here, based on definition, it should be x times density function, right? And obviously, in this special case, the limits will become what?
A to B.
A to B, and x, this is constant, 1 over B minus A here, dx, right? And then constant taken out, 1 over B minus A, and meanwhile, the result of integral should be what? X squared over 2, right?
Mm-hmm.
So A, B. And obviously this will give us what? X squared divided B, A give us what? B squared minus what? A squared. And times what? 2B minus A. Give us what? B plus A over 2. In other words, the mean value will be the middle of this interval. This also makes sense, right? Uniform means uniform literally means it should be uniform between A and B. Okay, so that's the reason why the mean value here should be what? A plus B over 2.
Mm-hmm.
That's the average, right? That's the middle point of this average. Okay, and meanwhile, we also need to determine the corresponding variance. In order to do so, we need to evaluate x squared first. Okay, so this will be equal to what? From A to B, right? X squared, 1 over B minus A dx. Okay, and then this will give us what? 1 over B minus A. Okay, this will give us 3x cubed, right?
Mm-hmm.
And A, B. So this will give us what? 3B minus A, and B cubed minus what? A cubed, right? And this result can be simplified because B cubed minus A cubed can be factored into what? B minus A times what? B squared plus AB plus A squared, okay? From algebra, okay? And 3 B minus A, now you can see equal to what? B squared plus what? AB plus A squared over 3, right? Okay, this is EX squared. And then the variance, let me look here. The variance will equal to what? The mean of X squared, right? Minus what? Mu squared. So this gives us B squared plus AB plus A squared over 3. And the mu is this guy here, right? B plus A over 2 squared. Okay? And this actually would give us, okay, let me complete this procedure here. B squared plus 2AB plus what? A squared over 4. Let's form one single fraction number here. This will be actually give us 12. This will be, let's say, 4B squared.
So it's B squared.
Let's say, okay, 4B squared plus 4AB plus 4A squared, right? Minus this guy, 3B squared. 6AB plus what? 3A squared. So this should be what?
Should be minus though.
Right. Actually, this corresponding to A must be squared. Okay? So this is a variance. Okay? Variance. And this is what? This is a mu. Okay? And a special case would be, let's say, when x uniformly between 0 to 1. Okay? And then in this case, mu, you can see here, A is 0, B is 1. If we plug in here, it's easy to see the mean should be what? Half, right? And then the variance, plug in here, A0, B1 should be 1 over 12, right? Okay? And here, the reason why I'd like to emphasize this special distribution is because many software packages, including Meta, provides bunch of random number generation functions, and we already use this function. So this function RAND actually is used to generate random numbers which follow this special distribution. Okay, so this is this function here, and now let's just verify actually this central limit theory using simulation. And basically, in this case, let's just do something like this: x1 plus x2 plus blah 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 plus what? x10. Okay, the sum of 10 random variables, and each of them follows uniform. Okay, so in other words, xk would be uniform 0, 1. Okay, and here let's just skip this division by 10. Okay, let's just directly calculate this guy here. We would expect the sum of these 10 random variables can be approximated by a Gaussian distribution, and the mean actually could be easily determined based on the information given here. You can see here, basically it says x1 plus x2 plus x10, right? And divided by n is 1 in this case, right? So the mean should be what? The same as what? The mean of uniform. So which means x should be roughly uniform here. So this should be what? The mean is 0.5, right? 0.5. And the hold on, this one. Okay, so this standard deviation, right? But the variance should be what? Sigma squared over 1, right? So hold on.
You have it on the bottom.
In our case, it should be actually it should be 10. That's n number, right? 10 times what? 1 over 12, right? That's a variance. and then square root, right? So this is what? This should be our, variance, okay? The square root would give us standard deviation, all right? And now let's just try to, first of all, let's just plot actually the histogram, corresponding to, say, x1, and then x1 plus x2, then x1 plus x3, x1 plus x2 plus x3, and so on. We are going to see the histogram will gradually change from what? A constant triangle, bell-shaped, until finally reach this Gaussian distribution, okay? And here, of course, it's just a histogram. In other words, we just use the numbers for each being for visualization. And in the second project, actually, you need to modify the histogram so that it can be very close to an actual probability density function. And your book provides solution regarding how to do this modification. Okay? The code actually is given in the book. All right, so that part you have to kind of like take a look at yourself, figure out how it works, okay, and then use the approach in your project. Okay. If any doubts regarding why and how this works, so we can talk. Yes.
So why do we include the n for the amount of?
It'll be easier for me.
Oh,
okay. Because I'd like to display, like, say, the histogram for x1 plus x2, x1 plus x2 plus x3, right? Blah blah until x1 plus x2 plus blah blah plus xn. Okay. Okay.
Okay.
And then I can use a easy loop to do this simulation.
Got it.
Okay.
Okay.
All right. Let's do this. All right, starting with 0, okay, at the beginning, and then we are going to use a loop. And in each iteration, we are going to generate 1 million random variables which follow uniform distribution between 0 and 1. And also we add, this vector to x, so which means x equal to what? X plus, say, R, A, and D, 1 and 1 million. Okay. For example, when k is 1, we end up having what? x1, right? When k is 2 is what? x1 plus x2, and so on. Okay. And then we'd like to display the histogram regarding x, and also we'd like to use 1,000 beings. In other words, the range of x will be divided into 1,000 parts, okay? And then histogram will display, the number of values for each being, okay? We'd expect, like, say, a Gaussian distribution finally in this process.
Professor?
And also, let's just pause, for each iteration so we can see clearly how this histogram evolves, right, from a constant into a bell-shaped Gaussian distribution. Okay. And okay, yeah.
So that rand 1 to the and then the million, that's just generating numbers from 1 to a million? Is that what it is?
This means it generates a vector with 1 row and 1 million columns.
Okay.
Okay. All right. So let's get started. Boom. All right. So see, this is the result of x1, right? Because we mentioned x1 is what? Is uniform. Okay. So PDF density function should equal to what? 1. Okay. And here, of course, I just mentioned this is not actual PDF. It's just number of values in each being. That's the reason why you see here, top equal to 1,000. Okay. So that's why. So it's because it doesn't make sense, right? Because it's uniform, right? We have 1,000 being, and each being has roughly 1,000 numbers. So 1,000 times 1,000 equals 1 million. Okay, it's uniform. Okay, and now let me push a button, and this what? This is the result for x1 plus x2, and now the PDF has this triangle shape. Okay, triangle shape. Okay, so you see here it's still between 0 and 1. Okay. And then this result what? This result, oh, okay, I made a mistake actually, because right now, because we didn't divide everything by 10, so this should be what? This should be mean value times 10, which should be the 5, right? Which means it should be 5.
Mean value times 10.
5. Okay, and here you see here, right now it's close to what? The mean value close to 1.5, right? It's already bell shape. Okay. Okay, so this is gradually, closer to the final stage. Right now the mean is 2, 2.5, 3, 5. Yeah, see, that's the final result. Okay, see here. Okay, it stopped execution. See, it's done, right? See here. So now you see it's a very a typical bell-shaped Gauss distribution. It's easy to see here. The mean value is here, 5 here. You see here, okay. And I just mentioned this is not an actual PDF, all right. And because PDF should satisfy one condition, which says the area enclosed by this bell shape should be what? 1, right? And again, I just mentioned, you have to follow the instruction given in the book regarding how to modify, this histogram so that it can become, actual PDF, probability density function. Okay. All right. So you see, to kind of verify. Okay, indeed, this new random variable x equal to sum of these 10 identical independent random variables. Okay, roughly, very closely follow this Gauss distribution. Okay, so let's also verify the corresponding mean value and variance. So we just mentioned, it's already verified. Say the mean is 5, right? It's very obvious. So let's just explicitly calculate its mean here by mean function here. So it's 5. Okay. It's very close to 5 because each time you run, you might get slightly different value. If you want to see more digits, we can use long format. And then again, let's see here, it's very close, right? Okay. How about variance? The variance should be actually, you see here, should be what? 10 over 12. Okay. So let's see. Okay. Remember, I made a mistake last time, so hopefully I didn't this time. So variance, this number, okay? And this number actually should be close to what? 10 over 12. So see here, it's close. Okay. So this is the reason why we engineers are so interested in studying Gauss distribution. Okay, and our cell phones actually, utilize this Gauss distribution a lot because the actual communication system, okay, is based on this Gaussian distribution assumption. Okay, so you see here, the power of math indeed sometimes great, okay. Especially when we design communication system, all right, the probability, plays a major role in such a design process.
How?
Yeah.
Do you know how?
Then you have to take communication.
Oh.
And here this guy just tell you, Gauss distribution is very important. And this simple, one line loop, one line, script just tells you, this important central limit theory. Okay, because when we do modeling, and here you see here, even like say 4 or 5 summation give us a Gaussian. Okay, that's the reason why a lot of noises or phenomena in engineering systems, including communication, can be modeled by this Gauss distribution. Okay, that's why. Okay, of course you can write one book for this Gauss distribution. All right, and here we just touch on the surface of this important distribution. All right, so. And also, I'd like to talk about a special case of this Gauss distribution, okay, where and we call this special distribution special case, standard. Usually called it standard normal distribution, and here. For standard normal distribution, the mean is 0, and the variance is 1. Okay, so this is called standard normal distribution. And in other words, in this case, okay, let me just and this will become what? This guy here. This become this guy here. E minus x squared over what? 2. Okay, so this will be the density function for the standard normal distribution. And meanwhile, the density function would become what? Would become this guy here. Okay, let me actually this has a special name I'd like to use here. Using this Greek letter, we use this Greek letter here. Okay, and it will be from say minus infinity to x, and 1 over square root of 2 pi e minus x. Let's use y also. So y squared over 2 and dy. Okay, so so this is the distribution function for the for this standard normal distribution. And here, actually, in a traditional probability or statistics book, you would expect a lot of appendix pages which list the values for this special function, okay? Because whenever you have a random variable, they follow this general Gauss distribution, all right? And then the probability actually, the function value, the probability here will be same as what? Will be same as this one here. Function value here, let's say x minus mu over sigma. So in other words, this new random variable, all right, would follow this normal distribution. And because it's easy to see here, if we say y equal to, say, x minus mu over sigma, right? And then you see ey equal to what? Ey will be equal to, say, E x minus mu over sigma, right? So it gives us what? Sigma can take out. And then Ex minus mu. Mu is a constant. The mean of constant is still constant. So equal to Ex minus mu. This is what? 0, right? Okay, Ex is mu. Okay, and meanwhile the variance, okay, will equal to what? The variance, let's say x over sigma minus mu over sigma. And here, you see here, you can treat this guy as a sum of two items, right? But only the first item is random. This is what? A constant. Obviously, the constant is what? There's no variance. The variance will be 0. That's the reason why it's what? Only sigma squared. When a constant taken out of variance operation, it should be squared. And then variance equal to what? Equal to 1. Okay? So that's the reason why, whenever you try to determine this probability or the function value at x here, and then you can use this function here, the distribution function for the standard normal distribution. Okay? Put another way, like here, still we have this same distribution, right? If you want to determine the probability, say x1, x2, okay? And then it should be this guy here, yeah. And then this equal to what? This equal to the difference between what? X2 minus mu over sigma minus what? X1 minus mu over sigma. Okay? So obviously, I'm not going to ask you to provide solution, actual value for this function value, to this function, because you're not allowed to use method in the test, right? But I'm going to ask you to represent your probability solution using this type of format. Okay? And the book use a slightly different definition. They call Q function. Okay? Which is very similar to this distribution function. Okay? We don't need to. Okay? Let's just use this, distribution function for this, standard normal distribution. Okay? All right. Any question? All right. So yeah, this is pretty much what I like to talk about and emphasize, Gaussian distribution. Okay, yes.
So this function, this is called the standard normal distribution?
Yeah, so,
okay.
And no, this is a distribution function for this standard normal distribution. Okay.
Right.
And in other words, this function will be translated to matter function will be what? Norm. Oh, sorry. Is that norm? Yeah, norm CDF, right? Norm CDF. And then x and the 0 and the 1. So this is still distribution function, right? But with 0 mean and unitary variance. Okay? So that's the meaning of this function here. All right?
So when the mean isn't 0,
and then you just, this isn't 0, right? Like for example, here. Then you just convert, like there's a conversion here. Because I just mentioned, if this is not 0, mean, and then I just mentioned, x, okay. Let me put it here. Then x minus mu over sigma will follow this G0, 1. Is that clear? Okay, so yeah, probably let me put it here, emphasize here. Okay, that's how we can convert this general Gauss distribution to this specialized, standard normal distribution, right? And because we all know, like say, in matter, this function is used to generate, this standard normal distribution. In other words, mean is 0 and the variance is 1. Okay? All right, any other questions before? All right, so now let's talk about our project. the idea of the second project is very similar to what I did here, in this simulation. It's also about how to verify if the sum of multiple identical and independent random variables could be approximated by a Gaussian distribution. Okay, the difference is in the project. Okay, each random value would follow a special distribution, which is called exponential. Okay, and definition is very simple. You can consult your book. Okay, and here also we need to pay attention to here. The key is how can we generate random variables follow this so-called exponential distribution, right? And the idea is like this. First of all, we have to generate U, which is uniform, 0, 1. Okay? And also, before we start with the coding part, you have to figure out the corresponding, CDF, cumulative distribution function, right? Let's say F. Okay, and then you also need to determine the corresponding inverse function. Inverse function. Okay, so you should know like what this mean, right? What is inverse function, right? For example, if y equal to ex, and then x equal to what? Then y, right? This is what? Called inverse function. Okay? And then in the coding part, first of all you generate, a uniform distribution, like say 1 million, for example, for one of those random variables. And then if we say x equal to this inverse function u, okay, in other words, this u would become the independent variable of this inverse function. Okay, for example, let's just say, let's use, okay, for example here, and then if this, say, this is fx, right? And then this inverse function here, and in our case, it was what? X equal to logarithm what? U. Okay, for example. Okay, so that's what we mean, let's say, U will be treated as independent variable in this inverse function here. All right? And like this is how you can create, this x would follow what? Exponential distribution. Okay? And again, this way you generate, say, 10 such random variables, right? Now you see the difference. And what I did at the very beginning, each of these random variables follows what? Uniform 0, 1 distribution, right? And here, in the project, xk follows what? This exponential distribution, okay? And here, this is the general idea regarding how to generate this exponential distribution. And your book also provides code regarding this process. And the code actually regarding generate a different type of distribution. Okay, but the idea is totally the same. Okay, and combining the idea I just mentioned in the class, and then like say the code given in the book, it should not be so difficult regarding this project. Okay, and then again you're going to experience the power of the central limit theory. Okay, so that's pretty much what we need to do in this second project. Okay, and you can consult your book regarding all the details you need to follow. All right, of course you can come to office for any doubts, questions. All right, so this is pretty much we'd like to talk about before the midterm. You can see I skipped quite a few sections. All right, like say the conditional probability in the second chapter. It won't be included in our class, okay? And then we are going to talk about, like, say, how we can model, multiple random variables, okay? And also we need to talk about, say, random signal processing, all right? Because, probability, we can talk about theory of probability, using even, 2 semesters, because that's not our focus here. So that's why I have skipped a lot of stuff, like, say, how to deal with the counting and the combination in probability. And those questions are pretty, sometimes it's pretty difficult, okay? But we are engineers, so we're not going to spend too much time to play those math games, right? We'd like to, see its application as soon as possible. But unfortunately, I have to take this a little bit slower pace, okay, so we can try to, enjoy this journey as much as we can, okay? Yeah, hopefully, all right. Okay? All right, so, all right, that's pretty much for the last lecture before midterm, okay? And now let's talk about a little bit about how we can prepare for the coming midterm, okay? So just, step 1, review your notes carefully, okay? Because stuff you can see here, obviously it will be very difficult just reading the book, right? Because you're not going to know, like, what's the mid, in our class, right? And the notes just tell you, okay, what's the most important concepts or topics we need to pay attention to, okay? And also you see here, some experiments might be kind of pretty vague, like in second example, right? Because it looks like most of people get lost in that question. I'm not going to give you such type of, experiment stuff, okay, in the test. I'm trying to give you a very straightforward, experiment for easy understanding, okay? But we still have to, review, like, say, basic concept regarding definition of probability, right? How to determine the probability of union A and B, right? And how to determine conditional probability, how to use Bayes' theory to determine, 2 total different conditional probabilities, and what is total probability, right? And what is, Bernoulli trials, okay? And then the definition of random variables, and then 2 very special functions. So probability distribution function and the probability density function, okay? How can we use those 2 special functions to determine probability and stuff like this? Of course, we also have to pay attention, probably just 2 special random distributions, which are Gaussian and uniform. Okay, even though your book covers much more, okay, you don't worry about those, special distributions, Rayleigh, those type of things. Okay, no need to worry about. Just focus on what? Gaussian and uniform. Okay, you must become very familiar with these 2. Okay, you see here I have tried to, make your life easier, in this preparation process. Okay, and yeah, so the due date for the project will be, I believe, a few days after the midterm. Okay? I'm not sure, I forgot, Sunday or Monday. Okay. All right. So of course, you also need to review, like, say, homework solutions. But some questions in the homework pretty, kind of difficult. It's difficult to understand, like, say, the meaning of the whole experiment, all right? But you're not going to see similar, vague experiments in the test, okay? So most questions will be very straightforward, okay? So just need to, have a complete understanding of those basic concepts, okay? And also, fortunately, you're allowed to have a cheat sheet, so that's good news, right? So, okay? So basically, it's going to be just like I mentioned in our syllabus, A4 size, right? You can put anything you want on both sides. Okay? Yeah. All right. The bad news is I taught this class many years ago, so you may not have the old test. That's the bad news. Okay? So I even lost all my old tests because I even switched from my old computer to new computer. So that's bad news. Because I taught this class the first time when I joined CSUN in 2004. Okay, and then I taught for quite a few years, and then the last time about at least 5 years ago. So it will be difficult for you to trace, to get old tabs. Okay. Yeah. Right, but nothing to worry about. Just basic stuff. Okay. All right. Any other questions?